Welcome to a new lecture of our Processing in Memory course. Today, after having introduced two other processing in memory architectures in previous lectures, we are going to talk about the Accelerator-in-Memory architecture from SK Hynix. This has been very recently announced, as we will see, in the past month of February. But before we talk about the details of the processing of the AiM architecture, let me introduce you, or let me remind you the two architectures that we covered so far. The first one was UPMEM, which was, by the way, the first architecture to be commercially available in 2019. This is a DDR4-based architecture where the DIMMs contain typically 8 or 16 chips, and inside each of the chips we have in the current generation 8 DRAM banks, and near each of the DRAM banks there is a DRAM processing unit or DPU. These DPUs are in order processors, and they have an in order pipeline of 14 stages. They read instructions from an IRAM and an SRAM based memory for instructions, and they read and write operands to a scratchpad that is called WRAM or working RAM. The second architecture that we presented in this course is FIMDRAM, or also called HBM from Samsung. This is based on HBM2 memory, and it's composed by, so the HBM2 memory, as you may remember, is a 3-stack memory that is composed by multiple layers of DRAM. Some of these layers of DRAM have been modified to introduce processing elements there that are called PCUs or simply PIM units. If we take a closer look at what we find in each of these DRAM layers in HBM PIM or FIMDRAM, we see that we find these PIM units that respond to a standard DRAM column commands, so they are compliant with a modified JEDEC controllers, and they execute one wide SIMD instruction commanded by a PIM instruction with a deterministic latency in lockstep manner. This SIMD operation operates on 16-bit floating point values at the same time. And here on the slide, you can see a representation of the DRAM bank composed by the cell array, and here we see column decoder, write drivers, and also input-output sense amplifiers from where the SIMD FPUs, from where the PIM unit are going to read operands, same as from these registers that you can see here. We are going to talk today about the AiM architecture from SK Hynix. This is, as you will see, it has certain similarities with the Samsung FIMDRAM architectures, but also as certain differences. As I said before, this architecture was announced in IESSCC conference this year in February, and it's based on GDDR6 DRAM. It's in a similar way as the Samsung architecture is targeted at machine learning and also high performance computing, big data computation, and storage. And this is the paper, and you can read here the complete title of this paper and the list of authors, and at the bottom you see you can find a link to the paper. And this paper starts with the classic motivation for processing in memory. The memory bandwidth is not enough for many machine learning workloads. So what they are proposing, what this work proposes, is extending the memory cells, the memory arrays with some logic units that can take advantage of the larger internal bandwidth that exists inside the DRAM, inside the memory chips. As you see here, the paper, or actually I think this slide is from their presentation at IESSCC, they talk about von Neumann architecture in the traditional processor-centric system that where we are limited in the external bandwidth of DRAM that connects DRAM to the processor, either a CPU or a GPU, and they compare it to a system architecture using processing in memory, where we can achieve much larger bandwidth in the logic units. We don't like so much this classification of von Neumann or PIM-based systems, we prefer to talk about processor-centric systems and memory-centric systems. As you can see, the difference between both is that in processor-centric systems, we only perform computation in the host processor, either a CPU or a GPU in this case, while in the memory-centric system, we extend memory with PIM capabilities in the form of whatever type of logic units. In the end, it's not completely different to the von Neumann model, because as you see here, we also have a communication unit that connects the memory array to the logic units. And if we take a look at the die, at this photograph from the die of the AiM architecture, you can clearly identify here 16 different banks, and each of them is connected to a processing unit, as you'll see. And here we have a more simplified representation, but where we can even see more clear the different banks from bank 0 to bank 15, as you can see, and also the processing units that are connected to each of the banks. As you see as well here on the slide, the processing units can receive data directly from their own bank, from the bank IO, or from these buses that we see here, coming from either outside of the DRAM chip, from other banks, or from these global buffer that we are going to present right now. So the global buffer is an extension of this GDDR6 die, where we find 2 parts, in total 2 kilobytes of SRAM memory, and these, as we will see, are intended to keep vectors that are going to be used in the machine learning workloads. If we take a closer look at the processing units, the first thing that we find here in the processing unit is an array of 16 multipliers. The input to these multipliers can come from either the bank IO, the own bank, or from the external buses, as you see, and each of the multipliers perform a 16-bit multiplication. After that, the partial results from the multipliers will be reduced using another tree, as you can see here. And finally, the value obtained in this accumulator can go through an activation function as well. We will see how. The way to control this architecture is by using some new commands that SK Hynix proposes to extend the existing GDDR6 commands. We will talk about some of these commands with a little bit of detail today, but here for now in the slide you can see this table where we identify bank activation commands, compute commands, and data commands. Actually, we start first with the bank activation commands. The novelty here is that it's possible to activate either 4 banks or 16 banks at once with these two ACT4 and ACT6 commands that have been included or added to the GDDR6 command set. And on the left-hand side, we see an example of 16 banks being activated. You can see how the same row is activated in the different banks, while on the right-hand side, you see the example for a 4-bank activation. As you see, the banks that are activated in this case are bank 0, 4, 8, and 12. In order to be able to perform these activations of up to 16 banks at the same time, it's important to get rid of one of the common constraints that we have in the DRAM operation. This is called the 4-active window. And essentially, this 4-active window imposes a constraint that essentially means that it's not possible to issue more than 4 activate commands in less than this T4 time. What SK Hynix engineers did in order to be able to perform up to 16 activations in this T4 time is extending the PUs with our reservoir capacitor. And yeah, as you can see here in this timeline, we can compare the normal DRAM operation where only 4 activate commands can be issued every T4 seconds or nanoseconds, while in the modified design for the accelerator-in-memory architecture, it's possible to issue new activate commands up to 16 during this time. And now let's talk about one of the let's say, I would say most important or representative command here, that is the MAC operation. The MAC operation, as you already know, is performed in the processing units. These processing units, as I said before, are composed by an array of 60 multipliers and another 3. And in order to fit these multipliers, we have to get weights and we have to get vectors. There are 2 different operations here, 2 different ways of operating, of performing the MAC operation. The first one is using the global buffer, this SRAM-based global buffer of 2 kilobytes that we have seen in the beginning. In this mode, it's possible to operate with 16, 4, or 1 processing unit per die. And in case that we choose this operation, the processing unit receive the data from the weights from the OM bank, from the DRAM cells in the OM bank, and the vector from the global buffer, as you can see in this slide. And the operation that can be performed on up to 16 banks at the same time is a matrix vector multiplication, where the matrix is this 2-dimensional organization of weights that we see here on the left, the vector and the weights coming from the DRAM banks, as we said, and the vector coming from the global buffer. And as you can see as well, the way that the computation is organized and assigned to the processing units is by bank. So in every processing unit, we will perform one of these dot products between the a row of the weight matrix and the vector. So that would be the computation for bank 0, this is the computation for bank 1, and this is bank 2 and bank 3. The results will be, in principle, stored in the accumulator, and at some point they can be either read or from outside, or moved to another bank, written to a different bank. And the other alternative for the MAC operation is the operation without the global buffer. And in this case, both the weights and the vectors come from the banks. And because both come from the banks, we cannot make use of the 16 processing units at the same time. It's only possible to use up to 8 processing units, because as you can see here on this figure, the processing unit receives data from the 2 nearby banks. In this case, or this configuration is similar to the way that Samsung HBM operates, because as you may remember, in the HBM PIM architecture, each processing element is connected to 2 banks, and one of the possible operations is receiving values from the 2 banks at the same time for the multiply accumulate operations. So if we take a closer look at how these operations are executed in this mode, the weights, so the weights are multiplied by the vector at let's say course. It's actually less operations at the same time, because we cannot work on all banks at the same time, right? So this is one example where in the first iteration we would be computing on bank 0, or the PU in bank 0, performing this dot product operation of the first row of the weight matrix and the vector, and bank 2 at the same time. And in a later iteration, we would compute on the remaining rows, like this one here, row 1 or row 3. So this MAC operation can also be can also make use of a bias. It's possible to add a bias that whose effect is essentially shifting the activation function by a constant, and it has been proven that it produces more accurate results in machine learning workloads and neural networks. So it's possible to pre-load a bias value into the accumulator. That's something we can do with a specific command, this write bias that you see here, and then after that we would perform the MAC operation. So as you see, we first load the bias. We can have up to 16 different biases, because we can have different biases in the different accumulators of the 16 banks. So this would be the bias for the PU in bank 0, and these are for the other banks, right? In bank 1, 2, and 3. And after performing the MAC operation, it's possible to use an activation function. This is something that also exists in the Samsung HBM PIM architecture. The thing is that in the Samsung architecture, as far as I can remember, only ReLU is the only activation function that is available, while here there are several other activation functions available as well, that we will talk about in a few slides. But for now, as you see, the accumulator can be, the content of the accumulator can be the input to this activation function that will output a 16-bit value. And as I said before, after having performed the MAC operation with or without activation function, it's possible to read from outside DRAM. In this case, it's possible to read up to 256 bits at a time, because, I would say, yeah, I would say it's in 4 cycles. It's something I don't really know, but the thing is that in one iteration with a single command would be possible to read 256 bits coming from 16 banks, 16 bits from each of the 16 banks, because the output of the MAC or the activation function is of 16 bits. And to do so, we can use 2 different commands, either this read MAC or this read activation function, and this would happen in successive cycles. As you see, first of all, reading the first 16 bits coming from bank 0. Another operation that is also possible to do in the MAC units is the element-wise multiplication. In this case, the tree adder is disabled, and the PUs, what they are simply doing is performing an element-wise multiplication of some values coming from either 2 banks or 1 bank and the global buffer, and the output goes directly to is written directly to a different bank, as we see here represented by this orange line, and this is the operation that is happening inside these PUs. Another interesting and probably will be pretty useful for programmers as well is this copy operation, that in some sense is, if not really a novelty, because these kind of techniques have been proposed in the past. I can talk about the row clone work from our group that was presented in Micro 2013, and actually I introduced in the first lecture of this course. As far as I can remember, Samsung HBM PIM also provides ways of moving data inside the HBM layers. But here is, I would say, out of these real-world processing in memory architectures, the one that has more clearly specified how this data movement can happen. And they enable 2 different commands, read and write, in order to read copy and write copy, in order to perform copy operations from one row, either in the same bank, so from one row to another row, either in the same bank or to another bank. And to do so, it's necessary to use these 2 commands, as I said. First of all, this read copy that will move 2 kilobytes from one row to the global buffer, and then the write copy to move back the contents of the global buffer to a different row, either in the same bank or in a different bank. And another, I would say, innovation and interesting novelty of this architecture with respect to the previous ones, in my opinion, is that it's possible to perform simultaneous computation and access. That is, it's something that cannot really be done in a fine-grained manner in the other PIM architectures that we present earlier. What this essentially means is that it's possible to operate on the PU of one bank and at the same time perform reads or writes to DRAM cells in other banks. And here you can see an example how the different commands are interleaved in the command bus. So first of all, we have here a read command to bank 4. Then this is a MAC. In this case, it's a single bank MAC operation in bank 0, and then sometime later another read to to bank 4. Right. So we assume that a row in bank 4 has previously been activated, and then the memory controller is sending repeated read commands to this row, in this case of bank 4, in order to read different columns of this bank, of this row. So now we are more or less familiar with how the AiM system is configured, and also what are the new commands that have been added by SK Hynix to the GDDR6 commands. Now we are going to take a look at some details of the microarchitecture that are in their paper and also their conference presentation, and I think that they are pretty interesting to discuss. So first of all, let's talk about the, let's say, more important and representative addition to the GDDR6 die, that is the MAC circuit that allows us to perform operations like dot product or matrix vector multiplication. This MAC circuit is composed by 16 multipliers, another 3, and an accumulator, and it operates using the bfloat 16 format. Here you see a figure of this MAC circuit. At the very top, we can identify the 16 multipliers. As you see, the inputs to each of these multipliers is one element coming from the matrix of ways, and the vector, in this case element B0, are the inputs to this lane 0 in the multiplier. Observe that this is essentially like a SIMD unit of 16 lanes. Each of these multipliers produces one result that is represented in the bfloat 16 format, composed by its sign, 8 bits of exponent, and 7 bits of Mantisa. This BF16 format, as you probably know, is very much used recently in neural networks and machine learning, because it provides a larger range than the classic IEEE 754 FP16, and it has been proven to be very efficient for deep learning training. So yes, so here is how these multipliers perform the multiplication, weights, times the vector, and these are the output of the multiplier. Now, after that, we need to reduce the 16 values that come from the multipliers, and to do so, we use these other 3. Here, as you see, it has 3 different levels. But one important thing that we are going to clarify in the next slides is how these other 3 is composed. But first of all, let me very briefly talk about prior work that has been proposed, like similar circuits for the MAC operation. This one is Newton, a paper that was published in Micro 2020. As you can see, it's a very similar organization. The memory cell array is accessed by this column multiplexer. 16 different values are obtained from the memory cell array, while representing the weights, as you already know, while the vector is coming from a global buffer, same as in the AiM architecture that we are presenting today. Here we have the array of 16 multipliers, and then we have the other three and the accumulator. It's not a surprise that this Newton has so many things in common with the AiM architecture, because in the end, it's coming from some of the same authors. But this MAC circuit was also presented even 2 years earlier by this other paper, MAC-DRAM, that also organizes the computation in a very similar way. Observe how different MAC units are in charge in different banks, are in charge of different rows of the weight matrix, and perform the multiply, accumulate, the dot product operation with the input vectors using MAC units and then another tree. And here you can see a little bit more detail about these MAC units. In particular, this MAC-DRAM paper is assuming 32 lanes in one bank, as you see here in the figure. And all these are different architectures and different circuits have in common that they use the SIMD processing paradigm. This multiply accumulate circuit. If you want to refresh about SIMD processing, I can recommend you this lecture from Professor Mutlu in spring 2021. More recently, in our heterogeneous systems course, I delivered a shorter lecture also on SIMD processing and GPUs. By the way, GPUs are also the kind of SIMD processors, and they have very interesting units as well for machine learning workloads. Are this so-called tensor cores that NVIDIA GPUs have. And as you see, as far as we know, these tensor cores are also SIMD units. And as you see, very similar. They look pretty similar to the processing units that exist in the AiM architecture and we are covering today. As you can identify here, the array of multipliers and then the other three. And this other tree is useful to perform very fast parallel reduction, and as we are explaining today. But if you want to get more familiar with this important operation for parallel workloads, I would also recommend you this lecture of about how to implement efficient parallel reduction on GPUs. So let's continue talking about this parallel reduction, and in particular how it's implemented in this other tree. There is some interesting hardware improvement that SK Hynix used in their other tree, is that instead of using regular floating point adders, as you may remember, in a regular floating point adder, what we have is first of all we compare the exponents and then they shift the mantisas as much as needed, depending on the difference of the exponents. And after that, we perform the addition operation in order to save some cycles, some energy, and also some area that can be useful for other uses, like, for example, extending the processing units with a reservoir capacitor. What they do is simplifying these adders by, first of all, including an array of shifters. And that's what they call the bank-wide Mantisa shift. Let's see how they do this. So first of all, because they have 16 partial results coming from the multipliers, from the 16 multipliers, first thing that we do is finding what's the maximum exponent in these from these 16 multiplication outputs. And then they obtain the differences in each of these shift lanes that you can see on the slide, they obtain the difference between the maximum exponent and the own exponent of the multiplication output that is the input to this shifter. And then they shift the Mantisa by the differences. They can perform all these operations in parallel because they have like as many shifters as SIMD lanes, and that's why they can perform all these operations in parallel. And finally, they perform the Mantisa addition. Here you can see one example. We have 16 output values from the multipliers. These are some example exponent values. What this small unit here does is comparing the 16 values, 8-bit values for the exponents, finds the maximum one. In this case, this one is equal to 15, and they calculate, first of all, the difference in this exponent comparator, the difference between the own exponent and the maximum exponent. And after that, they have a common exponent that is the maximum exponent for all the partial results, and they shift the Mantisa as much as needed. For example, in this first value, it's 3 bits. In this value here is 11 bits. And here you can see a simplified representation of how the computation time can be saved, because in the end, the exponent comparison and Mantisa shifting is only done at the very beginning, and after that is just necessary to perform these additions. So something important to mention as well is that, of course, here in this max circuit and the 3 other, we are operating on 16 values at once, but usually the rows in the weight matrix and the vectors will be longer than 16. So we need to use the accumulator to perform multiple MAC operations and multiple add-3 reductions and accumulate in the accumulator in order to obtain the final results. And to do so, it should be possible to issue successive MAC commands to perform multiple of these multiply accumulate operations between activates. And in particular, it's possible to issue up to 64 MAC commands between activations. It's a number that really makes sense because in each MAC command we operate on 256 bits. 64 times that is 2 kilobytes. That is the row size. Observe that between MAC and MAC is necessary to respect this interval TCCD, the column-to-column delay, as we can see here in this timeline. So we have first one activation, then we can start issuing MAC commands to different columns of the same row, and after having issued 64 of them, we'll have to pre-charge and then activate a new row, and then issue up to 64 new MAC commands. And this way, we will be accumulating in the first activation. We've computed the dot product of this part of the weights and this part of the vector in the second in the second activation, or after the second activation, we perform the dot product of this weight and this part of the vector. And this is also some, let's say, interesting extension as well of the PU that allows to save some writes to the global buffer. As you already know, the global buffer is going to hold the vector. This vector might be coming from outside, might need to be coming from outside, from the host processor, and of course, writing something from outside to the global buffer, it's going to take a significant amount of latency, because in the end, we'll have to go through the external memory channel, right? And in order to save some of these writes, it's possible to use these alternative latches that the MAC circuit contains. Near the, so in the accumulation circuit, there are two different latches such that it's possible to operate with two different vectors or keep partial results from two different vectors. While in a normal operation system without this multi-latch feature, we would need to first write vector 0, then perform the multiply accumulate operation of vector 0, or this part of let's say first part of this vector multiplied by this part of the weights, and after that performing. So we would need to write this other part of the vector in the global buffer, and then perform the multiply accumulate operation with the weights, and then we have to go again to vector 0 in order to, in this case, perform the operation with a different row of the weights. So as you see, in total, 4 writes would be needed. With the multi-latch operation, it's possible to first write V0 or perform first this computation W0 times V0, and then W2 times V0, and then write V1 and perform W1 times V1 and W3 times V1. And thanks to the fact that we have 2 latches here, it's possible to save 2 of these long latency writes. Okay, so now we are approaching to the end. Now let's talk about the activation functions. There are, as I said, it's also one interesting innovation of this architecture compared to the previous ones, because it provides different types of activation functions. In particular, there are 2 types, and for each of the types, there are several possible activation functions. The 2 different types are, first of all, those that can be calculated, like reload and leaky reload, and the second type are those that are based on the use of lookup tables. Now, what they are doing is extending the P unit near the MAC circuit. We have this activation circuit, and as you see, there are 2 possible paths here. The first one is for those activation functions that are calculated, like the ReLU and the leaky ReLU. The second, the other path is to for the loop-based activation functions. And as you can already see here, there are 2 steps for these loop-based activation functions. First of all, we need to read from the lookup table that resides in a DRAM row. There is a different one for the different possible activation functions, either sigmoid, yellow, tanh, or an arbitrary activation function that the user can load into one of these rows. And this is how it works. Each of the lookup tables contains 512 values, and there is a mode set register in order to select what's the activation function that we are going to use. For any specific value, this K is the output of the MAC unit of the MAC circuit. With this K, we can go to the lookup table and read let's say the immediate smaller and immediate larger elements of the lookup table. And based on these 2, FA and FA plus 1, we can interpolate and obtain a more accurate activation function value for the MAC result. And here is how it's done from the perspective of the memory controller. First of all, this command to select the activation function that is going to be used. After that, we'll have to activate the corresponding row for the corresponding activation function, and then perform the interpolation in the corresponding unit. So this is essentially all, let's say, main features of this AiM architecture. We have seen how the whole system is organized. We have discussed and presented some of the important commands in the extension of the GDDR6 command set, and we have also discussed some details about the microarchitecture. Here to finalize with this lecture, you have this comparison table as a summary of this presentation, and here we compare this work to previous work like the UPMEM PIM architecture or the FIMDRAM architecture. I wouldn't say that they are directly comparable. It doesn't really make much sense to compare a general purpose architecture like UPMEM to something like FIMDRAM or AiM that are targeted to a specific class of applications and are much more limited in the amount of different operations that they can execute. But still, I think it's good to recap on some of these parameters, because in the end, it's kind of an interesting exercise to understand a little bit more about the different architectures. So here you can compare them in terms of process, memory density, internal bandwidth, processing speed. Observe that this work is the one with the highest frequency, 1 gigahertz. This is essentially given by this TCCDS that is of value 1 nanosecond. Every 1 nanosecond, we can read 256 bits from one bank, and we can operate on them. So that's why we can say that the processing operation speed is 1 gigahertz, and this is also where, I mean, the peak throughput that we can achieve per PU and for the whole die. And that's all for today. We'll have more processing in memory lectures. In an upcoming Thursday, we will continue talking about other real-world processing in memory architectures, but we will talk about more things. We'll talk about processing using memory architectures and some existing prototypes, and we will talk as well about how to program processing in memory systems. In particular, we will focus for now on the UPMEM PIM architecture and probably more benchmarking and word loop characterization as well. So thank you very much for your attention. I'm really sorry.